students, welcome back to this section by Engineer R. Madhusudan Rao garu, who is Engineer Madhusudan Rao is the founder and managing director of Urja Energy Private Limited Company, Hyderabad, Telangana. Is a company specialized in energy engineering solutions. His expertise is in clean tech, heating, cooling, and ventilation solutions. He has 5 patents filed in these fields. He is pioneering in introducing many new technologies at a commercial scale of India. These technologies include radiant cooling, geothermal cooling, solar and waste heat based cooling. He has been at the forefront promoting low energy and healthy building in India. He holds a bachelor's degree in mechanical engineering from Osmania University in 1996 and has professional degree from Terry University and Stanford Graduate School of Business. He is currently the chair of technical group on radiant cooling in ASHRAE, that is in Indian Society of Heating, Refrigeration and Air Conditioning Engineers. He is actively involved in various R&D activities in this space in India. Thank you, sir. Please proceed with your presentations to your participants.
Thank you. Thank you for the kind introduction and good afternoon to everyone. Sir, I have one small request. If you can give me a little, background on all the participants.
Yes, sir. Yes, sir. This is the faculty development program. But this audience includes the research scholars. They are doing some PhD and some of the industrial participants also there. They are mostly interested on the poly generation, especially on the doing research on the solar energy, solar thermal energy and solar PV energy. Majority of the participants are from the institutes, industries and various faculty backgrounds.
Okay. Thanks for that. And from all over the country or a specific region?
It's a national, sir. Almost all the states, the participants came. It's a national level. It's funded by AICTE-ATAL, Government of India.
One last question before I start. So, how should I face this? How many minutes should I keep for presentation and how many for Q&A?
Sorry, sir. How many
minutes should I keep for presentation and how many for question and answers?
First you can proceed with the presentation, sir. After that, for completion of your presentation, maybe 5 to 10 minutes you can spend for the question.
Okay. So I'll take maybe half an hour, 35 minutes for the presentation.
Yes, that's fine, sir. If you want more interaction, that's also fine. Up to you. The total time is 1.5 hours. Okay. If you want to interact more, that's also it's fine. So it's up to you.
So what I do for the interaction is since my screen I cannot see, what we will do is maybe every 10 slides I'll stop, I'll give a break, and if people have any questions they can put it in the chat box. That's and fine. You or anybody else, if they can help and read that question to me, then I'll answer then and there instead of keeping everything towards that. Is that okay?
Fine, sir. Fine.
Okay. Great. Good afternoon again. I don't think many of you would have heard this term structured cooling. I'll delve into it a little deeper later, but what I wanted to do was first actually explain or present the data about cooling and India, where we are headed. Now, many of you may not be aware that the challenge that cooling poses to India in terms of decarbonization, in terms of energy need is actually far greater than even the mobility transformation of mobility from fossil fuel to electric vehicles. But somehow, due to lack of awareness, there is not enough attention being paid to this. There is some now, we see that government is waking up, there are new programs coming, but nowhere close to the amount of focus that is there in renewables or in mobility sector. Okay. So therefore, I thought first I will orient everybody towards as to how big a problem this is going to be for India. Okay. A problem, opportunity, whichever way we want to talk about it. If you see, as of today, there is no developed country in tropical region in the world. All developed countries, Western Europe, Northern America, Japan, even China, for most part of it, is not tropical, right? There are few city-states which are developed in tropical region, like Hong Kong, Singapore, Dubai. That's all. There are city-states, but no countries which you can call are developed. Now, why do I bring this up? I bring this up because today, where the affluence is there you do not have much requirement of cooling. Obviously, if you're above the Tropic of Cancer, your requirement for cooling is not as much as you would have it in tropics. Despite that, the bulk of the installed capacity today in cooling is in these developed countries. Okay. So today, if you see world over, okay, if I have to, point out, if you see somewhere around, we are what, 2025, somewhere around here, there are about little over 2 billion ACs all over the country. I'm sure all of you are able to understand the stacked graph. Okay. This one would be the complete of all countries. So little over 2.2, 2.2, 2.1, 2.2 billion. By 2050, India alone will have somewhere around 2 billion ACs. So whatever is today's installed capacity, India alone will have. Okay. If you see the graph, China is here, and the addition in China is not as much as the addition in India. So, and if you look at the rest of the addition that is happening, United States, more or less flat, a little bit addition. Okay. If you see Europe, Japan, and Korea, it's almost constant. There's hardly any addition. EU, there is some addition, not as much. So most of the addition is going to come from India and these other countries, Brazil, Mexico. So 80% of the future demand, today 80% of the installation, if you see till here, right, 80% of the installation is in non-tropical countries. In the coming 25 years, 80% of the installation will be in the tropical countries. Okay. Now, why is this?
Sorry, sir, 1 minute. Actually, y-axis is it a number of AC units in
Correct.
thousands? It is showing thousands, sir.
I mean, it is showing thousands. I'm sorry. This is thousands of thousands. So basically,
thousands of thousands. Yes.
Sorry, this is 2 billion. This is 2 billion.
Right, sir. Yes, sir. Got it.
Okay. So this is 2 billion. Okay. Anyway, so why is this important? This is important because one AC in non-tropical country is not same as the same 1 ton AC in non-tropical country is not same as one AC in tropics. Why is that? Let me take an example. If you go to, say, Munich or Paris or any of these places, first of all, most hotels do not have air conditioning, meaning cooling. Even if they have, the usage would be what? Maybe 15 days or 20 days in a year. Okay. Most of the time, weather is pleasant, non-tropical countries. But if you go to Kochi, Chennai, Mumbai, the air conditioning there is almost being used almost 12 months in a year. right? So the amount of energy and therefore the CO2 footprint of the same 1 ton of AC is at least 100 times more than, or I mean, if not 100 times, at least 10 to 20 times more than the same ACs installed in London, Paris, Munich, whatever. It does far more damage. Okay. And if we do not, and if they are not energy efficient, which in many cases it may not be, it does even further damage. That is why it is important for us to now understand ways we can cool ourselves without having such large energy footprint. Okay. Again, I'm repeating, it was not a requirement for all these non-tropical countries because their amount of usage was less. So even if it is inefficient and it is using a technology that is basically was invented to produce ice, it didn't matter to them. But to us who are going to be using this in tropical country, the operating expense is more, operating cost is far, far more than the main capital cost. So if you look at the life cycle analysis in terms of cost of AC or the cost itself, more than 90% of the cost in tropical countries will be of operating expense. Okay. If you look at commercial buildings in India, they may buy AC at 25,000 rupees per ton, but in a year they'll spend roughly 25,000 rupees per ton in electricity costs. Right? Whereas in a non-tropical country, the capital expenditure is more as a percentage in a life cycle cost analysis. Okay. That is why it is very important for us to start looking at technologies that can deliver us cooling at a significantly lower energy consumption, not marginal. I'll underline, not 10%, not 15% reduction, which is what our BE star rating is trying to do. It is required, but not enough. Okay. And this gives you a clear consumption of the energy that will be consumed for cooling. Okay. So in 2016, you are seeing how much energy tropical countries are consuming in terawatt hours. And by 2050, what it will be. Okay. We will be consuming far, far more energy soon. But there are not enough resources to cater to the hunger for cooling. Why will this increase? Two simple reasons. One, world is warming, you require more. Second is affluence will increase in all these countries. All of these countries, all including India, Indonesia, Mexico, Brazil, all of us are on a path to greater affluence. So people will start using more and more air conditioning, okay, which will create, we will jump from somewhere around 450 in 2016 anyway, 450 terawatt of kWh to 3,400, which is about nearly 8 times more. Whereas the rest of the world, the energy consumption will jump only by 50%. We are talking about 800%. So that's why it is important that tropical countries focus on technologies beyond the current conventional. The other challenge that causes more consumption of air conditioning in tropical countries is because we build our buildings using concrete and steel, right? Which means a lot more thermal mass is there. This thermal mass accumulates the heat. Sun comes, dumps the heat, goes away. Where does that heat go? It is retained in the building thermal mass. If you see a typical construction in, let's say, a Western country versus India, we use a lot more concrete and steel. whereas non-tropical countries, because they have access to timber, many of them construct using timber, otherwise stone, of course they use, but many of the time the amount of concrete being used is far lesser. The other reason is most of the tropical regions will grow vertically because of the population densities we have. Whereas most of the non-tropical regions expand more flat, horizontal. So if you have to go vertical more and more, most major cities today, no builder sees viability of a project unless it is 20 stories or something like that. I mean, in Hyderabad, where I'm from, we regularly seeing projects of 40 floors, 50 floors around. That can only be done through. So this also contributes to higher consumption. Okay. And as I was saying, if you see per capita income is low in these tropical countries compared to the non-tropical regions. So therefore, what will happen? The people in the countries which have low per capita income will try to buy an air conditioner, but since their per capita income is not high, they are more likely to buy very inefficient systems. For example, I was there in Mumbai yesterday. I was already seeing, I was passing by Dharavi. There are ACs available for rent for 500 rupees per month. Right? What are these ACs? These are refurbished, discarded window ACs, which probably consume 1.6 to 1.8 kilowatt per ton, compared to the efficient ones, which can consume 1. So more and more, while everybody is using 1-ton AC, but if we do not look at alternatives and depend only on vapor compression cycle-based systems, then we are digging, a big hole for ourselves to get it, right? Then there are public infrastructure. A lot of public infrastructure we have, bus stations, railway stations, everything. I mean, government buildings, right? Where it is not possible to air condition them because of 2 reasons. One is just the number of people coming in and going out. We make air conditioning almost impossible. Second, if we start air conditioning our public spaces, the cost of that will have to be borne by the public, right? Today, all our airports are air conditioned. And that's why all airports get to charge also the user development fees and other fees onto us. So it is fine for people who are traveling by air, they can afford. But if you make all our railway stations, bus station, everything also air conditioned, how will somebody recover? How will those entities recover that money, operational cost? So that is the point I'm trying to make here, that even if we are able to, solve this problem of cooling through air conditioning in many private buildings and all in our residences, in public spaces, how will we provide comfort? Because it costs too much to do air conditioning, and that burden cannot be put on people who are using that facilities. Okay? It's simply not viable. But if it's not viable, we can't say, if we are aiming to be, we are already 5th largest economy in the world and aiming to be 3rd largest economy. We can't say, if you go to airport, you will get air conditioning, but if you're taking train or bus, you will have to live with that heat. That is not the idea of a developed country that we would want. So such buildings also need comfort, which does not cost much. Okay. So this is the context in which I want to discuss further. I'll just pause here. If there are any questions, I'll answer. Otherwise, I'll proceed. I'll just wait for some 15-20 seconds. If there are questions, let me know. Otherwise, I'll proceed.
Yes, sir. Yes, sir. Dear participants, if you have any questions, you may unmute your voice. Otherwise, you may also text on the chat box. That's
So the entire purpose of this was to do a context setting, because many do not know that India is going to be the world's biggest market for air conditioning. That is why you see everybody, starting from Daikin, setting up new facilities. Recently, Bosch bought over the entire company, I mean, air conditioning company of Johnson Control, which owns Hitachi, right? So everybody's aggressively planning to set up more and more plants here, because this is going to be the world's biggest market for air conditioning.
yes,
From
yes.
nowhere. Today we have what? We have only less than 10% of air conditioning adoption, compared to China is close to 70%, Taiwan 90%, Japan 90%. So if at 10% we are having this problem with our electricity availability, you can imagine what will happen when it is more. I mean, go to 30%, 40%.
Sir, this structural cooling is mostly, is it electricity based or like a green building technology? Like, what is the energy source for the structure cooling?
Okay, I'll get into structure cooling. You will understand once. So, should I jump into structure cooling, or are there any other questions?
Yes, sir, you can proceed, sir. At the end of your talk, we may discuss, I think so.
Sure. So,
Yes, sir.
um, so what is very clear so far is we need affordable, sustainable, and affordable cooling. That is what we want, right? One approach, which is the current approach that I see, is how do I make this air conditioner more and more efficient, right? Which is why we see global cooling price and everything. With structural cooling, what we are saying is the current approach of air conditioning is to let the heat inside. If you really observe, what is really cooling? Cooling is nothing but taking the heat away. If I am regularly, if you take 1 ton of cooling, which is 3.5 kilowatt power, thermal power, which means every hour, what, roughly about 10,000 kilojoules of energy I'm taking away, right? 3.5 into 3,600, roughly, little over 10,000 kilojoules of energy I'm taking out of that space. 1 ton literally means that. If I'm taking away 10,000 odd kilojoules, 10,500 or 11,000 kilojoules of heat, it means that there is an ingress of that heat from somewhere, right? So what are we doing today? We are allowing that heat to come in and then using a device to take this heat away. Because internally, there is not much heat. As a human occupant, what is my addition? I'm adding only 250 watts of heat, sensible, and maybe another 200 or 50 watts of latent heat. The lighting and all that doesn't add much. Most of the heat ingress is because of the external factors. Solar heat is the source, and maybe ambient temperature through transmission gains, right? So what is our approach today? We let this heat come in and then use a device to take this heat out, right? Which is what we call cooling. What we are saying is there a better way where we don't let the heat come in itself? Okay. Now, traditionally, how did we do this? We used to, uh, 1 second, I'll come to that. Okay. So this is what in terms of the approach of cooling, structure cooling, is that the heat comes in through the structure. Therefore, if we cool the structure itself, which means if we take the heat away through the structure itself, then we will not require this energy guzzling equipment, to cool the space, which is nothing but removing the heat. So let's go back to basics a little bit. to understand this better. This is data from Hyderabad last year, 2024 data. Okay. And Delhi will also be same, Ahmedabad, Nagpur, all of them will be roughly the same. Okay. Now, what is that I'm trying to show you? This is May 13th, May 14th, May 15th. If you see the nighttime temperatures are somewhere between 25 to 30 degrees centigrade. 25 to 30 degrees centigrade. Summer night. Focus on the summer night at this point. Okay. It's not that summer day will be a little different, but I think in order for me to explain this better, I'll use the nighttime temperatures. Right now, it is sort of winter. Winter is getting over, at least in Hyderabad. This is Jan in winter. You will see that the afternoon temperature in winter is around 25 to 30 degrees centigrade. Okay. Now, I will take out the context here, whether it is summer or winter, and I'll create only two conditions. Okay. Condition one, 25 to 30 degrees centigrade ambient temperature, no solar radiation. Condition two, 25 to 30 degrees centigrade plus solar radiation. My question would be, when are you likely to use cooling, or when are you likely to require cooling in condition one, when the temperature is same and there is no solar radiation, or condition two? If I just present this as a problem of science without any context. Okay. Somebody wants to unmute and answer this question? So, okay, let me answer that myself then, right? If I say we will, I mean, as a student of science, the question, if it is posed to a student of science, they will say that you will require cooling here because there is the temperature ambient is same, plus, but you have additional solar radiation, therefore there is more heat ingress, therefore you would require cooling here. But that's not how we, behave. We don't use cooling here. We use cooling here, right? All the residences, air conditioning is blasting on summer nights. But there is no heat ingress. Where is the heat source from which you are removing from this room? You are removing roughly 11,000 kilojoules of heat using your air conditioner. If there is no heat in the ambient, no solar radiation, what heat are you really removing? What we are removing is the heat embedded and accumulated in the concrete thermal mass. So these are some of the thermographs. I'll explain this in a little more detail. The top three thermographs were taken on a summer night. Right? If you see here, the floor which is not even exposed to direct solar radiation, that temperature itself is about 35 degrees centigrade at 9:30 p.m. Other surfaces are also above that. So if you walk into a space, into a room, where the surface temperatures are between 35 to 45 degrees centigrade, it does not matter what is the ambient temperature, you will require cooling. Because when you are in a space, all you can experience is the temperature of the four walls, ceiling, and floor. That is all you are exposed to. You're not exposed to the outside temperature. This is what happens. And how do we reach here? When we took the same thermographs in winter, you will see, in general, the surface temperatures of the walls and the floor, everything is in mid-20s. So obviously, from here, it has reached to these temperatures. Now, this journey does not happen in one day. Unfortunately, most air conditioning professionals do the heat load as a instantaneous problem, not a time series problem. Okay. Of course, ASHRAE has clearly specified that radiant time series method is the way to actually quantify what is the heat load, because then you are taking into account the residual heat, from the earlier instances. But that is not how we do it. We don't consider. So if you see the journey from here to here, it will be half a degree, 0.75 degree getting added every day. So by the time you come to March or April, these will be the temperatures. Now, this is where we said, what if in summer we are able to maintain these temperatures? Then in that case, we should not be requiring cooling. That was our hypothesis when we first started looking at this data. Okay. And if you see world over, right, world over, that is how people built the houses or buildings, where direct solar radiation was never incident on the surfaces, on the external walls of the building. Whether they had, shading things like this or recessed walls. This was always the feature of the architecture earlier. Right? Today, architects don't have this luxury. We want to maximize the carpet area. Therefore, what do? We build buildings where heat is directly incident on the wall, external part of the wall, where inside we are occupied. And therefore, we experience this high surface temperatures. What many of us forget is what we experience is what is called operative temperature. Okay. I don't have that here, but if you look up about operative temperature, it is some function of the air temperature and mean radiant temperature of the surfaces that you are exposed to. Okay. Because they do make a difference, and you can clearly understand this when you go into, let's say, older buildings made of, let's say, stone of 6 feet or something, or go into a cave. In a cave, the surface temperatures inside or in a basement, right, are not varying because of the solar radiation, right? So what you experience is comfort, not air conditioning comfort, but okay. I put this picture here because this is where we got our inspiration from. This is in Hampi, Karnataka. This is called Lotus Mahal. There's a small well here. These are tanks. So earlier at that, this was about 400 to 500 years ago during Vijayanagara Kingdom. This water was lifted here using bullocks and all. There are ways to lift this. These are filled, and then there are terracotta pipes embedded in this so that the heat that this is accumulating can be drained away. Okay. This is the place for the queen to, occupy. So that is what we took care. We looked at it and said, since all these passive elements are now not possible, can we create an active system which all it does is flushes the heat, does not allow it to accumulate? Then in that case, we should feel comfortable inside a building without needing air conditioning, right? With fan and natural ventilation, which should be fine. So that is how we said we will do structure cooling. So we were already doing something called radiant cooling, but we adapted that because in all radiant cooling installations, we do use a chiller. We were looking at something where we don't have to use chiller. Okay. Even a best water cooled chiller will use what, around 0.5, 0.6 kilowatt per ton, plus all the pump, cooling tower, fan motor energy, condenser pump energy, all that if you add, that is a good 0.7, 0.8, 1 kilowatt per ton at best. But when you use cooling tower or sometimes even a water body, all I'm looking at is the heat sink. We embed a network of pipes in the building concrete. It could be either in the slab or in the screed. and you regularly circulate water in it to flush out the heat and not allow the heat to accumulate and build. For this, you don't need chilled water, you just need water at 24, 25, 26 degrees centigrade. That's it. There could be multiple heat sinks you can think of. The simplest one could be using a cooling tower. We use multi-stage cooling tower. It could be a water body. It could even be treated wastewater tank. I'm not saying we will use this water and circulate in this. I'm saying we will indirectly, we can dump this heat. We can use this as heat sink by immersing a heat exchanger or a network. So that's all structure cooling does. Does not allow heat to accumulate, flushes the heat so that people occupying the space, what we are doing, we are bringing down the mean radiant temperature. So let me go back here. If the operating temperature, if you see all ASHRAE documentation, everywhere they talk about operating temperature because that is what we experience. We experience the net result of the mean radiant temperature and the dry bulb temperature of the space. So if we are able to, let's say in this space, the air temperature is 24 degrees centigrade, but the surface temperatures are, let's say, 37, 38 degrees centigrade. And let's say operating temperature is a mean function of MRT, mean radiant temperature, and this. So 24 plus 38 divided by 2, that'll be what? 30 degrees centigrade will be your operating temperature. Right? 30 degrees is what you are experiencing. That is the operating temperature. But you are thinking that you are experiencing 24 degrees centigrade because you are looking at only a dry bulb temperature. But let's say if I'm able to bring this down to 24 degrees centigrade, okay, by flushing the heat, then what happens? I can afford to increase the air temperature to even 30 degrees centigrade or more and still feel the same comfort. Okay. And that is what we are trying to do, that it is not necessary that you can experience the comfort only at 24 degrees centigrade. If the main radiant temperature is lower, you can experience similar comfort even at higher temperature of 27, 28, 29, 30 degrees centigrade, which is how it used to be in the buildings which are older than 40, 50 years. They had a lot of thermal mass. The surface, inner surface temperatures were always lower. So even with fan and ventilation, they were just comfortable. You didn't need air conditioning. We are trying to mimic the same thing with an active system because to put so much thermal mass would be very expensive now. So all we are looking at is, a heat sink where this heat, which is being accumulated from solar radiation, can be dumped or flushed. Okay. So we had submitted this solution in response to a worldwide contest in industrial and commercial energy efficiency by MIT, Massachusetts Institute of Technology. And we were awarded, as the winner worldwide for this technology. And since then, we have implemented this in a few buildings. So this is a school in Delhi where we are doing it. But I'm just sharing what are all the configurations that are possible. If you have a pond, you can dump piping network into this or put a heat exchanger and still dump the heat. Many people approach us. We also install geothermal systems. They're willing to spend money to reject heat to the soil, but not willing to try this simple system, which is far more effective. Imagine rejecting heat to soil, which has lower thermal conductivity and also lower thermal diffusivity than water, right? And it is a limited, there's no other way for it to dissipate that heat. At least in an open pond, you have at least surface evaporation and night sky radiation to lose that heat. Okay. Swimming pool, this is what we are actually doing in a school in Delhi. We are rejecting this heat to the swimming pool. You get warm pool, never a hot pool. Please understand again, when I start, I'm going back here. When I start the system, the surface temperatures are still in 20s. So if every day I am not allowing it to go above 20s, my pool will, my surface temperature will not exceed 30, and my pool will also will never get temperatures in 30s. It will remain maybe in higher 20s, which is what we want. In the same school, we are also, using treated wastewater sump with which we are integrating. You can use cooling tower. Worst case, in some buildings where comfort is needed, we do integrate with chiller plants. These are some projects in which it is being integrated. This is a net zero building, but a very unique net zero building. See, anybody can achieve net zero. I can build a building, put any kind of air conditioning system. Let's say, I have a building in Gurgaon. I put air conditioning system. And all the energy that the building is consuming, I go to Rajasthan and put my power plant and wheel all that power to Gurgaon. I can achieve net zero. It's only a matter of how big a solar PV plant I need to put in Rajasthan or Haryana, wherever it is. But the uniqueness of this is we are achieving net zero with the solar plant installed on the rooftop of the building alone. No outside power is being wheeled here to achieve net zero. That's why this is a very unique building in the world. And the reason why we've been able to achieve is, of course, the building design, the architecture, all that matters. One of the main reasons is because we are able to use structure cooling here. Because in structure cooling, I end up using only 0.05 kilowatt per ton compared to 1.2, 1.5, 1.6. This is an architecture college in Vellore, where it is using with cooling tower. These are dormitories in Raipur. They are using chiller, but at a very high elevated temperature at 22, 23 degrees centigrade. So still, and the windows and everything are open, so natural ventilation happens. This is the school I was talking about in Delhi. This is the Sarvodaya school, government school, and this is the pool in which we are dumping all the heat from this structure. Okay. Quickly, I'll show you. This is the Telangana State Renewable Energy Department building. I'll just quickly show as to what is in summer. We do have chiller because this is an office. We also need to dehumidify. We run only one chiller. Rest of it runs on cooling tower. So what we are able to achieve is around 0.29 kilowatt per ton. This is unheard of. In monsoon, what happens is, since we are not able to get the required temperature from the cooling tower, the second chiller is also used, but at a very high elevated temperature. Even in that case, you are able to get around 0.37 kilowatt per ton. This is the school, government school that I was talking about, academic block and swimming pool where we dump the heat. In this case, there are just two pumps doing the entire job and is consuming only 0.09 kilowatt per ton. So that's it. These are some of the pictures from that, and I'll just stop here